so page 17, we are going to do the top problem together, and it's a little different. The physics is not hard, but maybe drawing a picture will help. Labeling some different places will help. So, as you work through independent practice, hopefully you're doing some independent practice. I highly recommend that before the exam next week, you do at least an hour of independent practice. And you're like, what does that include? So I was reminded this morning, Ms. Earhart, when are we ever going to do page 3 and 4? Oh yeah, we never did those. So let's put this as concept practice. You don't actually have to do any math. And so pages 3 and 4, you've got horizontal launch, vertical launch, and angled launches. And they'll ask you different things, give you different things, who spends more time in the air, who goes the highest. And so you can figure out, some of the concepts with these 2 pages. And then we're going to start 17 today. There's still that AP free response. This was on last year's 2021 exam. I do need to give you one little thing because we haven't studied energy conservation yet. The velocity when the biker comes off the ramp, the initial velocity is equal to square root 2gh. Now, it's a variable problem, so it doesn't simplify to one single number. And typically with variable problems, you don't plug in 10 for gravity. You keep it as g. So if you want to try this problem, you'll need that launch speed. Okay, question? Yes, I'm coming back to it. Yeah, the ball. And then there's NIMSY. So I'm just giving you independent practice options. And so NIMSY summary, if you want like the Cliff Note reminders. And then practice, this one is about a car turning a corner. And I wish I had waited on posting this one. I think it's still doable, but maybe that one feels weird because we haven't done circular motion yet. But definitely 23 to 24, you should be able to do, okay? And then if you continue to want more practice, here's an old problem set, keys on canvas, all right? So there's no absence of practice. So at least 1 hour of independent practice. I would say, can you do a horizontally launched object? Can you do a symmetrical angular launched projectile, not project, projectile? And then what about an angle launch that's not symmetric? And that's what you see in the lab, okay? We had a non-symmetric angle launch. Good deal? Independent practice, we got some ideas? All right, let's go back to page 17. So we're gonna do this top part. It says a ball is tossed through the air at an angle of 55 degrees above the horizontal. Pause, I'm gonna start my picture. Now, I am gonna start it on the ground because later they tell us it's on the ground. And so here's my ground. Here's my ball, whatever it is. We're gonna throw it up at a 55-degree angle. And it's gonna go up, 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 up. And I'm gonna stop it at the peak. Because for this problem in particular, there's no mention if it comes back down to the ground or if it goes off a cliff or what happens. And so we're just gonna stop at the peak. It says 3 seconds before reaching the highest point. Now, does that mean ground to peak is 3 seconds? No, we kind of go backwards in time. So from the peak to maybe this point, we know the time is 3 seconds. But 3 seconds before reaching the highest point, it's moving at a 30-degree angle with the horizontal. And so I'm going to bring in this third point or a mid-ish area point. And at that location, maybe the velocity is like so. And we know that the angle it makes is 30 degrees. If I can squeeze that in here. Okay. So that's what's given. Hopefully a picture helps. Note to self, if you read a problem and you're like, I have no idea what's going on, try to draw a sketch of what's happening. Okay, it should be similar to ones you've seen me draw, and then label what they're giving you. The question says, how fast is the ball tossed from the ground? In other words, what's this very initial velocity? Now I say very because here in a second, maybe we just care about the last 2 points, right? We kind of redefine where our initial and final are. And to help with that, the problem doesn't say this, but I think it's helpful. It starts on the ground. I'm going to call that point A. The midair point, I'm going to call point B. And then the peak, I'm going to call point C. And instead of writing initial final type, I'm going to say the velocity at A, the velocity at B, the velocity at C, just so we know where it's happening, okay? Subscripts should be your friend. They help describe. And so to get this hypotenuse, okay, all I know is the angle. But imagine it's just the variable, right? Don't we know that that initial speed has components? Yeah. It has a horizontal component and it has an initial component, a vertical component. What's going to happen as the ball makes it to point B? You have a different hypotenuse. Maybe I call that one VB. Vx is the same. And so maybe here, Vxb equals Vxa. But notice if you draw it somewhat to scale, not truly to scale, but somewhat, notice your VBy is less than VAy, right? And that should make sense. As the ball goes up, the vertical velocity should decrease. And when we get to the peak, what's true? Zero in what direction? In the vertical. And so VCY is 0. What about VX? It's the same as before. So I'm going to try and just tangent to the path, right? And so VXC is equal to VXB, which is also equal to VXA. VX, horizontal velocity is constant. Big projectile principle. Everybody good? So where do we begin? Well, to know the A hypotenuse, I need at least one of those components, right? You got to know one side plus the angle to find the hypotenuse. Well, I don't know either of those. The only thing I know is that the final velocity at point C in the vertical is 0. 3 seconds pass from B to C. Could we find the vertical component? Just focus on vertical B to C. That's where we're going to start. Long story short, we're going to work backwards, C to B to A. Okay. And so B to C, let's look at vertical. We know the final vertical velocity at C is 0. The initial vertical velocity at B is something we can solve for. We don't know it. But we do know acceleration in the vertical is gravity. I'm going standard sign convention. There's no reason to change. And they gave me the time from B to C. It's 3 seconds. And so our favorite kinematics equation, which one are we going to use? Oh, you want to use the third one? Number 2, really?
1.
Oh, 1, yeah. We don't know any displacement. We don't know the height change from B to C, right? And so we'll use the first one. So VF at point C equals VI at point B. And I'm just using some subscripts. If you come back and look at this, that way you know what's what. If you just use generic, right, it could be confusing. And so 0 equals what we're looking for. Yeah. And so the initial vertical velocity, but initial, you know, that can change. But the vertical component at point B is 30 meters per second. So I can go put that on my triangle in the B vertical component. Now, it turns out a little bit of a coincidence, 30 degrees and 30 meters per second. Don't start thinking angle and vertical component should always equal, okay? Coincidence. So how would we find the other two? Can we find the other two? So if I know the angles, and now we're looking at triangle B, we're going to do trig, not physics. I know the opposite side of the triangle, and we probably want the adjacent, right? Because it's adjacent Vx that's the same at each point. And so what trig would we use to find the adjacent? What trig function? Yeah, tangent. And so B triangle. So B, we're going to do some trig. Tan 30 equals opposite 30 meters per second over the adjacent, which is going to be our Vx. So we really don't need the hypotenuse at point B. And so to solve for Vx, you can look at it as a proportion, cross multiply switch. Careful how you put it in, but it'd be 30 meters per second divided by tan 30. Now I'm bringing in the unit because the other day I saw a student, I don't remember what period, I don't remember what the problem was, but they said something about distance on the vertical and velocity on the hypotenuse. When you do a vector triangle, they all have to be the same unit. Either all meter per second, meter per second, meter per second, or all meter, 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 later, Newton, 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 right? Forces. And so I'm bringing that unit in here just to prove that point. And so what is 30 meters per second divided by tan 30? 51.96. So I'm just going to call that 52. It's close enough here. So that's our horizontal velocity component. That's not what they asked us for. They said, what's the initial velocity at A? We're almost done, y'all. One more trig. Now, if we know that that's true for A and B, now I know the horizontal component at A is 52 meters per second. They want to know what the hypotenuse is, the launch speed. And so I know the adjacent. I'm looking for hypotenuse. Cosine. Last step for A. Cosine 55 degrees equals the adjacent 52 meters per second over VI, which is our hypotenuse. Again, to solve for the denominator, cross multiply switch. So VI, the hypotenuse, would equal 52 meters per second over cosine 55 degrees. And it's going to be a pretty big number. That's okay. 90.66, or we'll just call it 91 meters per second. And that is our final answer. And you're like, whoa, what just happened, right? And so here we did two trigs. We started with physics though at point C, came back to B, then came back to A. So we kind of worked backwards. It's not uncommon in physics to work backwards from one point to another. And so just be ready, you know, how did we know to do that? Look at your given, right? We knew more information at point C and B and had to work back to A. All right, part B is pretty good after this. What was the max height it attained? It was hit from the ground. So we can say initial height is 0, right? Ground. And max height would just be solving for the final vertical position at point C. So initial would be at point A. So what can we do from A to C vertically? What do we know? Final vertical at C is 0. And then what'd you say? Acceleration, negative 9.8, or here we're back on paper in physics land, so we can use 10, right? Lab, we do 9.8. Here we can go ahead and use 10. And we're looking for that final position. And if you remember, all of our kinematic equations need an initial velocity. And we're starting at A. And guess what? That's one side of the triangle that we don't know, but can we quickly find it? Yeah, so now we know the hypotenuse. We're looking for the vertical opposite component. And so if you remember, it's that initial velocity hypotenuse times sine theta. And so that 91 sine 55. And yes, you can also do tan. Yes, you can also do Pythagorean, since you know 2 out of 3 sides. So you actually have 3 options there to find the vertical component. But 91 sine 55 is, I don't know, it's 74.54. And again, it's meters per second. And so now we know the initial velocity, the final velocity, and the acceleration. We're looking for displacement. Question, do we know the time from A to C?
Would it be 2 plus 3?
Would it, you mean 2 plus 3?
Oh.
Is that what you said?
I said T.
T. Yeah, we don't know the first time from A to B. We know B to C is 3, but don't do things like, oh, let me multiply by 2. This isn't symmetrical. And so even though we could find time and then use one of our favorites, just suck it up. What equation does not need time? The third one. I heard one student say, that's my least favorite. Well, true story, you could find time, and then you could find the displacement, or we just go for this one. So 0 equals at 74.54 squared plus 2 times negative 10. And then the vertical displacement is really what we're looking for, right? We start at the ground, so whatever displacement we have is going to equal your final height. And so work it out, and I think it's going to be a triple digit, and that's okay, because we launched this thing at 91 meter sticks per second. It's very different than our lab where you had 3 or 4 meter sticks per second, right? So when you get your triple digit number, don't feel bad, it's right. What do we get? See, but it's supposed to be a big one. So you got to square the 74, subtract it to the other side, which will make it negative, but then you divide by negative 20. So you should get a positive answer. Yeah, I think it rounds up, right?
Yeah.
278 meters. So about 2 football fields. Whoa, that's okay. Physics land, right? Uh-oh. Huh? Yeah. Probably not a hand toss. Maybe we have some kind of cannon. Yeah, cannon launcher, air cannon. Questions on this one? The physics wasn't complicated, hopefully, but understanding what's going on is why I wanted to do it. Okay, so later, maybe next class, we try number 4, where we don't have any numbers, but it's about proportions. If you double the speed, what happens to the time? Okay, we'll at least do 2 or 3 maybe. All right, so now you can use this time to work on lab with your lab group.